On July 1st, 2025, astronomers spotted a faint interstellar traveler, 3I/ATLAS, racing toward our Sun at 58 kilometers per second. But just weeks later, a second object, 100 times larger, erupted into view, SWAN R2, with a tail 5 times wider than the Moon. Now both are converging near the Sun, heading toward a point that orbital simulations say makes a direct encounter almost inevitable. Is this a staggering cosmic coincidence, or a consequence of intent? The truth could rewrite our understanding of what enters our solar system, and why. The evidence is mounting, but the deeper story is only beginning to unfold. 3I/ATLAS entered the record books on July 1st, 2025. The ATLAS Survey telescope in Chile flagged a faint, fast-moving object, barely a kilometer across, yet racing toward the Sun at 58 kilometers per second. Its path is hyperbolic, not bound to the Sun, confirming its interstellar origin. The orbital solution leaves no doubt. 3I/ATLAS will never loop back. It will cut through the inner solar system once, then vanish into deep space, never to return. Initial measurements set its closest approach at 1.8 astronomical units, well outside Earth's orbit, closer to Mars than to us. That safe distance ruled out any threat, but the numbers still raised eyebrows. A nucleus smaller than most known comets, yet moving with extraordinary speed. Hubble imagery narrowed the size estimate to less than 1 kilometer, making it a true lightweight among cosmic visitors. For context, Halley's Comet is more than 10 times wider. Spectroscopy revealed a composition rich in carbon dioxide, with traces of water vapor, cyanide, and atomic nickel. The coma, the glowing shell of gas and dust, shone brighter than expected for an object this small. Observers noted the dominance of carbon dioxide emissions, a rare trait that hints at a cold birthplace far from any star. The presence of atomic nickel, while unusual, fits within the growing catalog of interstellar oddities. Yet the overall chemical fingerprint remains distinct from any solar system comet on record. Atlas's trajectory is steep, slicing nearly perpendicular to the ecliptic plane. The velocity and angle suggest it originated from far beyond the Oort cloud, ejected by forces unknown, perhaps centuries or millennia ago. Its arrival triggered a global scramble. Ground telescopes, space observatories, and amateur skywatchers all raced to gather data before it slipped behind the Sun. For many astronomers, the numbers fit the profile of a reconnaissance probe, a scout, not a heavyweight. Small, fast, and hard to catch. Its timing, path, and unusual chemistry make it a prime candidate for further study, especially as questions mount about what, if anything, might be following in its wake. C/2025 R2, now named SWAN, enters the record with a presence that dwarfs every other comet of the decade. The first detection lands on September 11, 2025, when the SWAN ultraviolet instrument aboard SOHO picks up a signal so bright it triggers an immediate alert. Within hours, astronomers verify the sighting, a tail stretching more than 2.5 degrees across the sky, 5 times the width of a full moon. That kind of scale is not just unusual, it is nearly without precedent in the modern era. The initial brightness, magnitude 7.4, surges to 6.9 in less than a week. By September's end, SWAN threatens to outshine every star in Virgo, visible to binoculars and even the naked eye from dark sites. The numbers keep escalating. Photometric data shows SWAN brightening from magnitude 11 to 8 in under a month, a leap more typical of a major outburst than a steady approach. Its closest approach, calculated for October 21, 2025, comes at 0.27 astronomical units, about 40 million kilometers from Earth. The orbital solution, confirmed by the International Astronomical Union, places its period at over 22,000 years, a cycle so long that the last human witnesses would have lived in the Ice Age. But it's the tail that captures attention. Ultraviolet imagery from SWAN shows a structure not only long but dense, with plasma emissions extending far beyond the dust envelope. Ground-based observers confirm the tail's width, 5 moons, end to end, a corridor of glowing gas and charged particles visible even through moderate light pollution. The sheer volume of material, and the rate at which it's being ejected defies easy explanation. Standard comet models predict tails a fraction of this size for objects of similar mass. SWAN, on the other hand, seems to operate on a different scale entirely. Speculation grows as the data accumulates. Some astronomers describe SWAN as a fortress, a massive, shielded body, possibly designed to withstand the harshest conditions near the Sun. Others point to the rapid brightening and massive tail as evidence of an unusually volatile composition, perhaps rich in supercooled gases or exotic ices. Yet the object's energy output, estimated at thousands of gigawatts, pushes it further outside the boundaries of known comet behavior. For now, SWAN stands as the most colossal and enigmatic visitor in the solar system, its true nature hidden behind numbers that refuse to settle into any familiar pattern. Spectroscopists trained their instruments on SWAN and found a puzzle that refuses to fit. The light, split into its atomic fingerprints, revealed a dominance of nickel. Sharp, unmistakable lines at 3,414 and 3,524 angstroms, each far stronger than expected. Yet iron, usually the companion metal in cometary spectra, was almost entirely absent. This is not a calibration trick or a fleeting artifact. Repeated exposures from Keck, VLT, and even JWST confirm the same pattern. The nickel-to-iron ratio stands at more than 20:1, a value that stretches the boundaries of known comet chemistry. For comparison, even 2I/Borisov, another interstellar visitor, showed nickel and iron in rough parity, with cobalt trailing far behind. Here, cobalt tracks close behind nickel, further skewing the balance. No solar system comet, not Halley, not Pan-STARRS, has ever displayed such a stark elemental split. Iron's usual spectral lines at 3,720 and 3,859 angstroms barely rise above the noise floor. Some researchers suggest that in nature, such a composition could only form in environments colder than 20 Kelvin, or in the aftermath of a supernova's selective condensation. Others raise a different possibility. Engineered alloys, designed for resilience or reflectivity, might favor nickel and cobalt over iron for their resistance to corrosion and high-temperature stability. The data is clear, but the cause remains open. As the debate unfolds, the focus shifts from static composition to the strange, shifting behavior in SWAN's tail, a dynamic signature that may hold the next clue. SWAN's behavior refuses to settle into the patterns astronomers expect from even the most volatile comets. Light curve records from September onward show not just a steady rise, but a jagged modulation, peaks and valleys spaced almost exactly 3 days apart. Spectroscopists tracking these pulses note that each crest coincides with a rapid surge in plasma emission, followed by a sudden drop. The magnitude of each event is staggering. Calculations estimate more than 10,000 gigawatts released at the height of each flare, rivaling the total output of Earth's entire electrical grid. That's not a gentle outgassing. It's a forceful periodic venting that some dynamical modelers compare to the firing of a low-thrust engine. Force modeling teams at the Paris and Tokyo observatories ran simulations using these light curve pulses as input. The result? SWAN's trajectory wobbles, deviating in subtle but measurable ways from a purely gravitational path. Each pulse imparts a tiny but distinct delta V, a change in velocity that over weeks nudges the object's course by hundreds of kilometers. The timing is too regular, too cleanly separated from random solar activity to be dismissed as mere coincidence. While mainstream comet science points to episodic outbursts or cryovolcanic jets, a minority of researchers raise the possibility of controlled propulsion, an engineered adjustment, not a natural accident. For now, the data stands: a 3-day rhythm, massive energy release, and a trajectory that refuses to obey the ordinary rules. SWAN doesn't just blaze across the sky. It moves with purpose, as if responding to an unseen signal or internal clock. The question isn't just what SWAN is made of, but what, or who, is steering it. Mass tells its own story. 3I/ATLAS, the so-called Scout, weighs in at just over 1 trillion kilograms, roughly the mass of a small mountain, yet spread across less than a kilometer of rock and volatile ice. On the other hand, SWAN commands 3 orders of magnitude more, a quadrillion kilograms, a difference that puts it closer to the scale of a large asteroid than any comet in recent memory. Astronomers crunching the numbers found the size ratio staggering. SWAN outweighs ATLAS by nearly 1,000 to 1. That imbalance isn't just academic. It's the difference between a lightweight probe and a fortress built to survive the worst the inner solar system can offer. Shielding comes into play as SWAN approaches the Sun. Solar wind data from the SWAN instrument on SOHO, cross-checked with ground-based magnetometers, shows a distinct attenuation pattern as SWAN's coma expands. The plasma tail doesn't just trail behind, it wraps around, forming a cocoon that absorbs and redirects charged particles. The effect is measurable. Instruments detect a local drop in solar wind density, as if SWAN is carving out a protective bubble in the heliosphere. For a natural comet, that level of shielding would require a shell of gas and dust far thicker than observed. Some researchers point to this as indirect evidence of a dense, possibly metallic core, a structure designed to take the brunt of solar radiation head-on. Agility, too, separates the two. ATLAS, nimble and small, displays subtle course adjustments, tiny but detectable shifts in velocity that suggest either rapid outgassing or, as some speculate, controlled maneuvers. SWAN, by contrast, moves with the inertia of a juggernaut. Its trajectory is steady, less affected by solar tides or outbursts. The fortress, in this analogy, isn't built to dodge, it's built to endure. Observers watching the solar wind drape around SWAN's expanding envelope note the sharp boundaries, the way the plasma tail seems to harden under solar pressure. The numbers support the metaphor. ATLAS scouts ahead, light and quick, while SWAN follows as the shielded bulk, absorbing what the Sun throws its way. With both objects set to disappear behind the Sun, astronomers brace for a blackout, knowing that whatever happens in that hidden corridor will be shaped by these very differences in mass, shielding, and agility. October brings a blackout that mission planners have dreaded for months. On the morning of the 8th, both SWAN and ATLAS drop below 5 degrees of solar elongation, too close to the Sun for any ground-based telescope to track. Even the largest observatories, from Mauna Kea to the VLT in Chile, are forced to stand down. The glare overwhelms every sensor. The sky itself becomes a wall of light. For 2 full days, no optical or infrared instrument on Earth can collect usable data. The blackout is total. Space-based assets fare no better. Solar orbiters' wide-field imagers are programmed to avoid pointing within 12 degrees of the Sun, a hard-coded safety margin against blinding. SOHO's SWAN and LASCO cameras, designed to monitor the solar wind and outer corona, cannot resolve the comet's nuclei or inner tails at such tight angles. Parker's solar probe, built to withstand the Sun's fury, lacks the imaging power for distant targets. The result is a gap, a window where both objects slip beyond the reach of every scheduled instrument. Behind the scenes, emergency memos circulate through ESA and NASA control rooms. Engineers debate whether to risk retasking Solar Orbiter, even for a single off-nominal exposure. The risk is real. One misstep could damage a billion-euro mission. Meanwhile, radio astronomers prepare to scan for bursts or anomalies, but solar interference threatens to drown out any signal. For the critical window of October 8th to 10th, even the most advanced planetary defense networks are effectively blind. The blackout sharpens the stakes. If either object were to alter course, split, or transmit, no one on Earth would know until the Sun moves on. The suspense is not theoretical. It's written into the mission logs and contingency plans. Astronomers, skeptics, and theorists alike are left waiting. The next signals we receive could rewrite every assumption or confirm that the universe is stranger than we dared imagine. Avi Loeb, Harvard astrophysicist and Project Galileo founder, sees the timing and chemistry of SWAN and ATLAS as more than coincidence. SWAN's 22,554-year orbit, he notes, mirrors ancient climate cycles and the dawn of civilization. For Loeb, the odds of 2 objects arriving from opposite sides of the sky and converging near the Sun within days are too slim to ignore. He wonders if Earth's radio leakage triggered a response. SWAN is a probe, its nickel signature and heavy shielding designed for survival near the sun, maybe even as part of an interstellar network. David Jewett, a leading comet scientist, reads the same data differently. Nickel-rich spectra, missing iron, and a coma thick with carbon dioxide all point for him to natural chemistry. Comets from the coldest regions can trap exotic ices and metals, he argues, and the apparent timing is just a statistical fluke, amplified by gaps in our observation record. Jewett's models show that missing data can swing probabilities wildly. The 22,554-year cycle, to him, is just a number, no hidden message. Between these views, the debate grows. Engineered probe or cosmic accident, signal or noise? Three signals stand above all others in the search for proof. First, a tightly patterned radio burst, encrypted, repeating, or modulated, would be the unmistakable hallmark of intelligence. No known comet or asteroid has ever broadcast such a signature. Second, a sudden maneuver. If SWAN or ATLAS changes course in a way that cannot be explained by outgassing or gravity, the data will speak for itself. Abrupt delta 5, measured in real time, would force even the most skeptical astronomers to reconsider the rules. Third, geometry. A resolved structure, regular, symmetric, unmistakably artificial, captured in high-definition images from Hubble, JWST, or ground arrays. Not a blurry blob, but a lattice, a grid, a shape that nature does not produce by accident. Each test is clear, decisive, and within reach of today's instruments. The blackout window in October means the world must wait, but the moment these objects reappear, every telescope and radio dish will be watching. Which proof would convince you? A message, a maneuver, or a machine? The answer is yours. Vote in the pinned comment, and if you want live coverage as the blackout lifts, subscribe for the next signal. The next chapter may depend on what we all decide to look for. On October 8, 2025, both 3I/ATLAS and SWAN R2 will vanish behind the sun, unobservable from any ground-based telescope for nearly 2 days. Their paths, confirmed by the International Astronomical Union and the Jet Propulsion Laboratory, show a convergence that is rare in recorded cometary history. SWAN R2's tail, measured by SOHO/SWAN, to span 5 times the apparent width of the full moon, and its nickel-rich spectrum remain unexplained by standard comet models. While some experts, like Avi Loeb, point to engineered origins, others, such as David Jewett, argue for rare but natural cosmic processes. No direct evidence of artificial signals, abrupt course changes, or geometric structure has yet been observed. As of today, the true nature and purpose of these objects remain unproven. What happens during the 2-day blackout will be determined by the data, recorded in real time by the European Space Agency and NASA missions. Until then, the facts stand. 2 unprecedented objects, 1 convergence, and a solar conjunction that leaves the next chapter unwritten.